All right, we're talking about rational exponents today and radicals, so let's just jump right in. So what does the square root of 100 mean? And this might feel really, really simple, but what does it mean? Well, it means that there's some number that when we square it, it equals 100. And what number is that? Well, you all know that that number is 10. It has to be 10. And what I want you to think about, though, is this is actually kind of like if we're saying, okay, we're trying to get to 100. And when we're doing exponents like this, we're multiplying, we're counting in this multiplying type of way. And this is, we take some number and we multiply it 2 times because, you know, the square root is 2. So we multiply it 2 times to get to 100. What does that number need to be? What do we need to multiply twice to get to 100? And we know that that would be, we would need to go times 10 times 10. So the square root says, what does that number have to be if we just take 2 steps to get to 100? So if we look at this next one, what does the fourth root of 16 mean? You know, most of you can say, well, that means some number x to the fourth equals 16. There's some number that I put to the fourth and it's going to equal 16. And we know that that number is 2. X has to equal 2 because 2 to the fourth is 16. So I want you to think, though, about this on a number line again. And I want you to think that means that we're getting to 16 and we're going to count by multiplying some number 4 times to get there. We're going to get there in 4 steps this time instead of 2. And so what number do we have to count by to get to 16 by, you know, taking 4 steps? Now, remember, normally when we think of counting, we're adding, right? We're adding 2 every time that we count. But really this time, because we're doing exponents, we're multiplying every time. So what number do I have to multiply? Well, I have to multiply times 2, times 2, times 2, times 2 to get to 16. So what's the fourth root of 16? Well, it's 2. So what about what's the fifth root of 3,125 mean? Again, this means that there's some number that when we raise it to the 5th power, it equals 3125. And you might know that that number is 5 because when we take 5 to the 5th, it equals 3125. But we can also think of this one on a number line. Here we have the number 3125. We're going to take 5 steps to get to that number. We're going to multiply by the same number every time we take a step. And so how big are these steps? What are we multiplying by every single time? Well, we're multiplying by 5. So the fifth root of 3,125 is 5. All right, so what does the fourth root of 10,000 mean? Well, what number, when raised to the 4th power, equals 10,000? And you might know that this is 10 because 10 to the 4th is 10,000. We'll just think about this again on a number line. We have 10,000. We're going to take 4 steps to get there. And every step we're going to have to multiply by 10 to get to 10,000. So you may be wondering why I'm complicating this so much and why I can't just say, well, what's the fourth root of 10,000? It's because we're going to learn about these things called fractional exponents. And I want you to look at these and ask yourself, what does 4 to the 1/2 mean? And if you've ever seen these before, you already know what it means. But in Algebra 2, in our class, we haven't actually seen this yet. So just think about, what does 4 to the 1/2 mean? And I want you to come up with something that you know is wrong, an answer that you are sure is wrong, and think about why it's wrong. So my answer maybe would be, well, I know that 4 to the 1 is 4. And I know that 4 to the 0 is 1. And I know also that 4 squared is 16. So I know for a fact that 4 to the 1/2 can't be 20 because it's too big. I see a pattern going down as I get the exponents smaller. So 4 to the 1/2 probably has to be somewhere in between 4 and 1. So a wrong answer could be 20 because it's too big. So let's look at this pattern and decide what we think this is. So here we have 4 to the 4th is 256, 4 to the 3rd is 64, 16, 4, 1, 1/4, and 1/16. So we wonder where would 4 to the 1/2 fit? And we realize they would fit right here, right? 4 to the 1/2, 1/2 is somewhere in between 1 and 0. So 4 to the 1/2 is probably somewhere in between 4 and 1. But what is 4 to the 1/2? Well, let's go back to that ridiculously complicated number line. And here we have 4. And let's try to get halfway there. Let's count in a timesy sort of way. And we're going to get halfway there. Well, what number, if I multiply it by itself 2 times, is going to get me to 4? I'd have to count by 2's, right? I'd have to multiply by 2 by 2, right? So what is 1/2 of 4, or 4 to the 1/2? Well, 4 to the 1 is all the way to 4, right? But what's half of the way there? Half of the way there is just 2, because we just multiplied by 2 one time. So 4 to the 1/2 is 2. All right, I want you to take a look at these calculators, and I want you to just notice and wonder some things about them right now. So 25 to the 2/3 equals the same as the cube root of 25 squared. Do you see a pattern emerging? Do you see that a fractional exponent and a radical actually have a very similar pattern? So here is the way you convert. As we just saw, 4 to the 1/2 is the same as the square root of 4. So here we have a radical, and remember, if you remember back to Algebra 1, this is your index. That's your index. And this is your exponent. Okay, so when we switch from a radical to a fractional exponent, you're going to go E over I, or like E-I-E-I-O. That's how you're going to remember it. So the exponent goes on top and the index goes on bottom, just like we saw in 4 to the 1/2. So the square root of 4, remember anything we don't have an index for is automatically a square root, so it's automatically 2. And this is an invisible exponent of 1. So we did 4 and then the exponent over the index, so 4 to the 1/2. So let's practice that. Let's simplify each of these. Let's write them as the other way around. So 125 to the 1/3. So we could write this, remember that's exponent over index. So our index is 3, which means our exponent is 1. And we have the cube root of 125. What is the cube root of 125? You might know that that's 5. But again, we could think of our number line, and we could think here's 125 on our number line. And we're going to, it looks like we're going to make 3 jumps to get there. 1, 2, 3. So how many jumps, or what would each of those jumps have to be worth if we were counting? Well, that would have to be times 5, times 5, times 5, right? And so if we look, what is 1/3 of the way? 1/3 of the way to 125. 1/3 would be right here, so it would be 5. You might feel like, well, that's a lot of work to get there, and it feels like that, but you'll see that it actually is sometimes easier. So 1296, this would be the 4th root of 1296. So what is the 4th root of 1296? Well, it is 6, because if we took a number line, we wanted to get to 1296. Whoa, man, that just went nuts right there, right? 1296. And we are going to take some jumps. We are going to take 4 jumps. 1, 2, 3, 4. What is, well, let's see. First, we'd have to be multiplying by 6 each time, right? To get to 1296. And what is 1/4 of the way there? Well, it's times 6, right? So it's 6. All right, this one is the cube root. This one changes to the cube root of 27. And what is the cube root of 27? Well, it's 3. This one is the fourth root of 256. So what to the fourth equals 256? Well, that's 4. Let's head on to the next page. So let's ask ourselves now, okay, all these other ones we've seen are just like the cube root or the fourth root or whatever, right? Well, so what is 64 to the 2/3? Well, let's rewrite it. We know this is EI. Oh, so we have exponent over index. So that means this 3 is going to go on the outside because it's our index. And the exponent's going to go on the inside, or like this. It doesn't really matter. We could write it the cube root 64 squared. Either one is fine. Okay, so let's think about what this is. So we could evaluate it. We could take, well, what's the cube root of 64? Well, it's 4. And then we square that, which would be 16. So we could do that. But we could also think about this logically on our number line. We could say, well, here's 64. Hoping I got some equal subdivisions there. And this 3 tells me we're going to make 3 jumps to get there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ah, yes, the OCD person in me really wants these to be even. Okay. 3 equal jumps. Okay. We made 3 jumps to get there. And what would each of those jumps need to be to get to 64? What times itself 3 times gets us 64? Well, that would be times 4, times 4, times 4. And so then the final question we ask ourselves is, what is 2/3 of the way? When we're counting in this way, what is 2/3 of the way to 64? Well, it's this piece and this piece. So it's 4 times 4, which is 16. So either way works. Excuse me. I really like the visual of the number line. It really helps me see what we're really thinking of, but you can always rewrite it as a radical. Okay, so what is 36 to the 3/2? So we can rewrite this. Remember, this is exponent over index. So this is going to be the square root of 36 cubed. So we can figure this out. What's the square root of 36? It is 6. And what is 6 cubed? It's 216. Or we could figure this out with the fractions. So here's 36. And this 2 tells us we're going to jump. We're going to make 2 jumps to get to 36. So 1, 2 jumps to get to 36. And so what do those jumps have to be? That's times 6, right? And this says, what is 3/2? Okay, so here's 1/2. Here's 2/2. Well, 3/2 would be 1 more jump times 6, right? It would be 1 more times 6. So times 6 times 6 times 6, which is 216. So let's just practice just a few. In class, we're going to play a game with this. Let's just rewrite this one. This would be the cube root of 17. This one would be 2 times a to the 1/3. This one is going to be this exponent over index. So the cube root of m squared. This one's going to be h to the 1/5. This one's going to be 29 to the 1/3. This one is going to be x to the 1/3, y to the 2/3, because exponent over index, right? X has an exponent of 1 and y has an exponent of 2.